is Tom Brown, and today you're going on a trip into the borderlands of science. We're at our top secret lab hidden in the vast wastelands of Southern California, and today we're going to take a look into the possibilities of free energy, what is electricity, what's really happening. There's a lot of talk about free energy these days, a lot of researchers really trying to do things, and we feel that there's a lot of misdirection and false paths. And what we're going to show you today is some actual research and verifiable results and some phenomena which just doesn't fit into the standard textbooks. I'd like to introduce the people that are here. Right next to me is Eric Dollard, co-director of Borderland Sciences, along with myself. And he's designed and built a lot of the equipment here, and he's the author of 5 published papers to date on extensions of the work of Nikola Tesla's high-frequency researches. And next we have Michael Knox, design engineer and student of ether physics, who has built a lot of the equipment here and been generally supportive of getting Borderland Labs together. Next to him we have Steve Ellswick, who's the editor of the Tesla newsletter for the International Tesla Society. Steve's come out here from Colorado to view the experiments here and be an independent observer. Next to him we have Chris Carson, who's the chief electrical engineer at the University of California, Santa Barbara, and he's done quite a bit of input here at the lab and been generally supportive. And over here next to Eric, last and certainly not least, is Dave Franklin, Eric's longtime lab assistant and veteran observer of weird electrical phenomena. And also Peter Lindemann, who is running the camera, and you will see as we go on with the video, who has developed some of the equipment here. Peter's a director of Lindemann Laboratories in Santa Barbara, and he's a researcher into free energy, extreme low frequency waves. The question often comes up, what is electricity? Well, I can honestly say I don't know, but I have done some investigation into it, and working with Eric Dollard, I've come to a few basic understandings. One of them is that electricity is a polar phenomenon, that there's actually 2 poles to it. The one pole, which is what people just understand electricity as being, is magnetism, but there's another side, what we call dielectricity. Eric's found in his work that dielectricity is related to what Wilhelm Reich called the orgone energy, or what we understand as the mass-free energy of the ether. And I'd like Eric Dollard to explain a little more, since that's about all I know.
So basically, we start off with the phenomenon of electricity, breaking it down into its 2 constituent components. Okay, one which we're all very familiar with is magnetism, and a device which exhibits magnetic phenomena is the inductance coil.
Hold it up sideways. Yeah, there, okay.
Which can be shown in different positions here, which we'll get into a little later. You know, magnetism is usually your more thermal, dissipative, or decaying type of force, and is best symbolized by the colors brown or red, or the lower end of the spectrum. Basically, magnetism is a phenomenon associated with the retardation and decay of electricity. Then we have its counterpart, dielectricity. Now, this is a forgotten part of electricity, which is very important because it's really where it comes from, and is often called mistakenly the electric field. But technically, the electric field is a combination of the magnetic and dielectric field. So dielectricity is stored in a device usually called a condenser or capacitor, which looks similar to the coils in many regards, and we'll get into this a little later, exactly how they relate. So symbolizing dielectricity by the Greek letter psi, symbolizing magnetism by the Greek letter phi, then the electricity is basically, I use the lowercase phi for this, the product of the dielectricity and the magnetism. In the magnetism, we can call it more of a direct spatial type of phenomena, but the dielectricity is more of a counter space type of phenomena. Now, if we look at our devices here for working with each, we have the inductance coil, a magnetic device. Okay, we can look at this on 3 axes. We can look at it this way, we can look at it this way, and we can look at it like this.
Get a real tight shot of it. Could you keep holding it up here? I want to get a real close up here and focus in on it here. Great. Right. Now you could turn it.
Let me turn it this way.
Yeah.
Now that's just a coil like a spring, correct?
Right.
Right. Okay.
This is a device for the storage and return of magnetic energy. Now this is a device for the storage and return of dielectric energy. Okay, starting off, look at it this way. First we gain very little by turning it this way. And then to spread the plates out for view, we can look at it like this.
Can you hold it obliquely so we can see that it's a complete cylinder to, like on the other side here? Yeah, there we go. Yeah, there. There, that's the one.
Okay, now for comparison, we connect these two things together, produces what's known as an electric oscillation. Now if we look at these things together, we notice some immediate similarities in this direction or this direction. Now if we look at it endwise, taking the plates out again, then we notice we have a complete contrary type of situation. One is like a complement to the other. Where the space is open in this, the space is full in this. But both of them involve basically what's called subdivision of conducting material, or so-called conducting materials we'll see later is more appropriately called an obstructor or reflector of electricity. And what has been regarded as the insulators in actuality will turn out to be the conductors. And hopefully with the low power apparatus we have here today we'll be able to demonstrate this. We're only right on the verge of the necessary power. Okay, now there's nothing better than direct experience with these things to see what's really going on, so we'll get to this quite shortly. We can take our electromagnetic induction, which produces electromotive force. Electromotive force is the rate of production or consumption of magnetic induction, or magnetic lines of force, or the many names that are available for this basic phenomenon known as magnetism. So we have lines per second, time being seconds, and this being the number of lines of force of magnetism. You know, what we have over here is a charging choke out of a large radar. Now, these devices possess very large quantities of magnetic induction and are insulated for extremely high voltages. So we can show this production of electromotive force quite readily. Over here, we have a dielectric inductor or capacitor or condenser. Now, this device here comes out of a very large intercontinental shortwave transmitter, and again is capable of producing very large quantities of dielectric induction, or in this case, very large currents. Now, the electromotive force we'll experience here in the magnetic side will be roughly 15 to 20,000 units, known as volts. Over here, we will have roughly between 200 and 1,000 units of dielectric induction called amperes. Now, both of these are considered very large quantities, but this is necessary to make it physically observable. We'll start off with the dielectricity, hoping all of our tubes stay in here. Actually, we got the magnetism going first, so let's get that going while I warm this up. So the first thing we need is time. So we have a time generator in here. We'll turn this on, and you can hear the clicks, seconds. Now down here, we have an apparatus for converting, or in this case we can say producing electrical energy. Energy that's purchased from the utility company and converted into what's called direct current for producing the magnetic field in the inductance coil. You know, we have variable auto transformer here for bringing up the current. Right now I'm supplying 100 volts to the inductance coil at a current of 300 milliamps. Now when the circuit's broken, it will raise the frequency here. Try to bring our rate up. Give it more power. So now we'll get into the complement of electromagnetism. Now the viewers may have also noticed there was severe interference appearing in the television set. Now this type of discharge has the uncanny habit of producing what Tesla was using in his one-wire broadcast of power. All you need connected to this coil is just one single wire to ground, and this thing will send an impulse down that guiding path, which we'll get into other electronic apparatus. Now what happens normally, this encounters itself or appears in situations of switching transients on power lines, but most notably is the refrigerator in the household, which has a large inductance coil to produce the magnetism. Well, this inductance coil, when the thermostat breaks the circuit, has to discharge its energy. And this energy is broadcast through the neutral wire and often will appear as a very loud pop or bang in stereo amplifiers and other types of things, even with the volume control turned down. So the semiconductors and the amplifiers serve as detectors of this kind of energy and will pick it up quite readily and will often be damaged by it if its transient is severe enough. Okay, we'll warm up the dielectric apparatus here. Okay, now we have a similar situation, but rather than breaking a series circuit, what we're doing is providing in shunt pulses of electromotive force from an induction coil here to charge this capacitor, which then is instantaneously short-circuited by a spark gap. So what we have here is an apparatus that discharges by short circuit, where this apparatus discharged by open circuit. We'll slowly bring this up. And now you notice that this discharge is blue and can be brought up to a much higher speed before starting to misfire. And most significantly, it will be noticed, even though it's hard to see with the lighting here, end of the wire didn't melt. Okay, now the sound of this was many, many times louder than this. The brilliance of the light was many, many times higher. Even though the energy going in this case, comes from a smaller power supply. So we can start to see that dielectricity is moving in the direction of what we want with regard to free energy. It tends to magnify the phenomena and accelerate it, where this tends to retard the phenomena and produce decay of it. So hence we have our two complementary forms of induction, which together produce electric induction and in its various forms is utilized today. Briefly reviewing, we have the electromagnetic induction, which is time and magnetism. In this case, we have the time and then the magnetism. The dielectric induction, again, is flux per second, or the rate of production or consumption of dielectricity, in complement to magnetism. In this case, again, we had another time generator, and we had a device for storing the appropriate induction and changing it. So that basically concludes our two complementary components of electricity and how they interrelate both geometrically, as we can see by direct physical observation of the devices for utilizing these phenomena, and then their direct industrial application with industrial size apparatus to bring the energy level up to a point where it can be readily seen. And the combinations of these two inductions, along with the dimension of time, produce what's called energy, which is a very fundamental quantity in electricity. But our most fundamental quantity in electricity is not energy. Mistakenly, this is taken as fundamental, but is the product of dielectricity and magnetism, which is the flux of electric induction. And as these were the laws of electromagnetic induction and the laws of magnetodielectric induction, there exists a third law, the law of electric induction, which by algebraic manipulation of these figures will show is the rate of production or consumption of electric induction. So hence this is our most fundamental quantity in electricity, which we will call simply electricity or electric induction. So that basically concludes our introduction.
Eric's interesting experiment brings to the forefront a concept known as counter space. We have the general space, which we understand. Here we are in space. But what's counter space? Well, we can understand counter space as the plant existing inside the seed before it comes out. I mean, we put a seed into the ground and out grows this plant. Eventually it decays and dies. We see the decay here in the electromagnetism, and all power and generation today comes from the side of decay. On the other side, the brighter spark, the blue spark, the opposite pole of electromagnetism, the dielectricity, comes from what we call a counter space, the other side, which is the living side where things grow. This is something that everybody out there should be looking into. It's a very open area of research, and we're just beginning to understand it. Now we're going to see a demonstration by Peter Lindemann of a rotary parametric transformer, which is also known as a variable reluctance device. This is a novel type of electrical generator which was conceived by Peter Lindemann, built by Michael Knox, and Eric Dollard helped put the test apparatus together. And you're going to see a demonstration of seemingly over unity, and we'll see if it is or not. Here's Peter Lindemann.
Thanks, Tom. First of all, I'd like to describe for you the inner workings of the machine that we're going to see in the test apparatus that we're going to be testing for the next 20 or 30 minutes in the film. This is a diagram of the device, which we're calling, for the purposes of this filming, the rotary parametric transformer. And basically what it is, it's very similar to an ordinary transformer, except that to produce the output, we have a physically rotating member in the center here, which causes the oscillations in the magnetic induction in the output coil. Viewed from the top, we have 4 direct current poles facing an inner wheel. The inner wheel has 2 sections of iron laminations in it that is rotatable, so that it periodically produces a magnetic circuit between 2 of the input magnets, leaving the other 2 input magnets in a non-closed magnetic system. And then as this piece rotates, it continues to change the magnetic conductivity of these circuits, which is what we call reluctance, the change in the resistance to magnetism in these circuits. Now what this does when we oppositely magnetize poles that are 90 degrees in opposition to each other, that these 2 magnetic members in the rotor, which look like this from the side view, when in alignment with one of the sets, they will magnetize in one direction. And when it is rotated 90 degrees, then it will magnetize in the opposite direction. And this big stationary coil, which is the 5th coil of the system, which is wrapped around this moving member, but itself does not turn, it sees the changes in the magnetic alignment of these iron sections in the rotor, and thereby generates an alternating current output. Just give you a brief discussion here. The wiring schematic of the apparatus which you're about to see has inputs and outputs. The input for the motor, we have a variac which takes the wall current and changes the voltage. We put that through a wattmeter, and then we change that into direct current and filter it so we take all the ripples out of it, and we use that to drive our brush style drive motor, which is over here on the top of the apparatus. We energize the field coils with another variac, and that energizes a low voltage DC power supply. So we vary the input power to a low voltage DC power supply, and that gives us low voltage direct current to energize the field coils, which are these types of units around, and there's a fourth one around the back. So the output of this then comes from a fifth coil, which is difficult to see on this movie, but it's in here, it's wrapped on the inside, this gray area where I'm pointing. And it's wrapped all the way around on the inside. And the power comes out of that coil, and it goes through a wattmeter and amp meters and voltmeters. And it goes over here to this switching panel here, where we can either put a resistive load or a capacitive load. And in this case, the resistive load would be the light bulb here, and the capacitive load is this bank of capacitors, which we can flip in and out of the circuit just by throwing a switch. Now this is a more complete actual wiring diagram of exactly what we're doing with the output. The output coil goes through the wattmeter, and these various switches are our switching panel here, showing the resistance loads and the capacitive loads. We also have switches to open up the circuit or short circuit. So we can create a short circuit right through here by closing these switches, or we can open various switches and drop our current through capacitive and or resistive loads. So this is the circuit that we're going to demonstrate for you. Now, one of the things that has been missing in all the free energy demonstrations that I've ever seen on videotape or photographed and written about in books is basically a discussion of what we'll call total efficiency. Now, the total efficiency of a system is quite simply the total output of the machine divided by the total input. And when we say total output and total input, we're talking about watts. You may notice the ice cream man going by, but it doesn't give away our location. Now, the total efficiency of this system will not demonstrate over 100%. However, there are losses in the system which we can calculate. And so we can look at what we'll call the working efficiency of the system, which we can call the total output divided by the total input minus the losses. And we'll look at these main losses. This one, which is E squared G, which we'll just call the windage. And the I squared R losses, which Eric will help explain in more detail as we get into the demonstration. So today, when we calculate the total efficiency and the working efficiency of this device, we expect that this, for this machine here today, we expect that this total efficiency will be less than 100%, but that this working efficiency will be greater than 100%. And now, okay, what we're going to do is we're going to turn this machine on, and first we're going to look at the total input under no load power conditions. So what this says is power under no load, NL, equals the E squared G plus the I squared R, where the E squared G is the windage and the iron, and the I squared R is the copper. And we're going to turn on that field, and instead of having to calculate all this, we're going to be able to read that directly on the watt meter, just how much power it actually takes to make up all these losses. So we're going to turn this on now. And you may notice that the thing makes a little bit of noise. So I'm having to shout over the machine. But this meter reads 100 volts direct current to the drive motor. This variac is reading 100 watts on a scale of 0 to 500 watts. And this is a DC ammeter which reads 0 to 10 amperes, reading approximately an ampere. So this is our no load. This is our no load power. So we're just going to write this down. It's 100 watts. Okay, next we're going to energize the field coils. We can do that by just throwing this switch here. Now the thing makes more noise. Makes more noise. The output's approximately 120 volts AC, but we don't have any load on it yet. So this output watt meter shows 0, and the AC ammeter shows 0. But the extra load that comes from the field power on brings the total input power up to 180 watts. Okay, now we're ready to run the power output test. So we've condensed our figures. We've condensed our figures to the power under no load input we read off the watt meter at 100 watts. The power with the field coil on was 180 watts. And we have set our little red marker here at the 180 watt level. So I'm going to turn the field coils back on again. And you see this comes approximately back up to where we had marked it originally. And now we're going to put on the load. Let's start with the light bulb. So you want to throw those on, this one, that one, and the next one. Okay. So that's demonstrates a resistive load. And now we can take a look at our meters and see that this one is now drawing 182 watts output. 182 watts out on the watt meter. And this is now reading 348 total input. Okay? Did you get close-ups on these meters?
Yes, I have.
Okay.
Eric, could you explain the distinction between the waveform with the load on and load off?
Here with the load on, the self-inductance of the machine predominates. And what this does is take the higher harmonics that were seen in the unloaded waveform and cause them to be dropped as a back EMF across the self-induction of the output coil of the machine. So basically, the more you load the machine, the more you're going to be attenuating your harmonics. The discussion on that is necessary at this point. Now, normally, what we've used here is we've used basically the best switchboard instruments available, and these are the industry standards. Basically, the utility companies use these to precisely meter the flow and direction of power in an electrical system. But these meters are designed for relatively pure sinusoidal waveforms with usually no more than 10 or 15% harmonic distortion. So we have to realize, of course, that under no load, and even with the load on, the distortions are going to influence the meters slightly. But what we have, and when we get into our self-criticism of our interpretations of results here, we have radio frequency amp meters and radio frequency voltmeters, which are waveform insensitive and only measure the effective values of the occurrences. Now, one thing I'd like to point out here is quite often, and to quote somebody, what do you want, volts or amps? Well, neither of these things are electricity. One is the law of electromagnetic induction, and the other one's the law of magnetodielectric induction. Neither of them is electricity. That's why we've incorporated the electrodynamic instruments here, which take the product of both the so-called EMF or volts and current or amperes. And this is the true indication of what's going on. Now, what we'll do a little later is we have a variable resistor bank here, and what we're going to do is tune the resistance bank to the impedance of the machine to produce the maximum output of power. But one thing I've noticed here is I believe that by serendipity, this light bulb here has turned out to be precisely the impedance of the machine, because you may have observed that the voltage dropped from 120 to 60 volts, or 1/2, which is fairly indicative of a precise impedance match. Now, normally an electrical generator of substantial size is a constant potential machine, and when you put a load on it, there's no drop in voltage. It's appreciable. You can keep on loading and loading and loading. That's called the constant potential machine. Now, in the old-time days for street lighting circuits, they used to have what are called constant current machines. And basically, the more resistance you would put in series with the circuit, there'd be no effect on the current, and the current remained constant. Two standards have been adapted in the industry. Constant potential systems are rated in 120 volts, and constant current systems are rated in 6.6 amperes. Now, we have a machine here that rides somewhere between constant current and constant potential, and therefore has indefinite impedance. A constant current machine has an indefinite impedance, and a constant potential machine has an indefinite impedance. The impedance of constant potential is 0, and the impedance of constant current is infinity, or you might say the admittance of constant current is 0. One thing I'd like to point out also when we were talking about dielectricity and magnetism, is most people have seen electrical apparatus heavily encased in iron, and other bulky magnetic type of housings. But here, this machine has to be made entirely out of dielectric material, where the power is all needlessly consumed in eddy currents. So we see we started to make a fundamental design departure here. Engineering requirements have caused a new type of material, dielectric material, to be incorporated in this machine.
So, you want to explain these figures?
So basically then, if we take and subtract our no-load power, which is that power that's lost independent of what the machine consumes, and we're left with the residual, the power that's transformed by the machine, we end up here with 168 watts left over that's going into the machine, minus that's due to the losses. Our output power was 182 watts, so our total conversion efficiency here then is 108%. Now this opens up a very interesting can of worms. Okay, now it can be easily disputed that, well, what you've done here is you've built a simulated electrical resistance. And by loading the machine, you've taken the simulated electrical resistance out of the machine and placed it as a real electrical resistance in the load. Therefore, you're not generating any free energy. But we still got a bit of a problem. Where's the heat? We're dissipating energy in here. Why isn't it getting hot? So one thing here with these free energy devices, rather than laboring to produce so-called free energy, which is really not a very good term, you might better off call it anti-thermodynamic energy or cinetic energy, or a number of names that haven't been fully resolved yet. But anti-thermodynamic, as we will see in our final demonstrations, is the best name for this. We will actually produce the phenomena of life synthesized by dielectric induction. So what we have here is probably our first application of this machine would be losing electrical energy rather than producing it. Okay, now if we look at the ways we have to lose electrical energy, particularly in electronic devices where all of the electrical energy is lost, 100% of the electrical energy is lost in every electronic device because of the nuclear nature of electrons and protons and all the things involved there. It's naturally a decay loss phenomena. As an example, we'll take our oscilloscope here, a very effective space heater, especially when it's nice and warm outside today. Pulls a lot of power, makes the power company meter spin real fast, but the light output of this scope is roughly 1/1000th of the energy going into the scope. So we can say it's 100% losses. Now we can take another loss device, the clutch in an automobile. We have to put an energy impedance between the engine and the load, and the clutch backs up the energy, or might say it produces a back EMF, and it gets hot. But if we could apply this technology to produce the loss of electricity without heat, then we've made a definite step forward, without breaking any laws of physics as to where the energy could come from or any of these things. But getting out of that realm a little more, if this thing is a resistance, the resistance being positive if it's consuming, or if it's a free energy machine, the resistance being negative, but nevertheless what we have here is a device that varies inductance with respect to time. Okay, now as every engineer knows that inductance with respect to time, which typically appears as a quantity called omega L, for henries per second, turns into ohms. Ohms of reactance. So what we have here is a synthetic resistor. And I leave it up to the audience to choose whether this synthetic resistor is positive or negative. Nevertheless, we have come up with an anomaly. So what we're going to do here is check the light bulb, see if it was the right impedance by inserting a variable resistance bank, and see if we get any greater power out by tuning for an energy resonance between the machine and its load. Also, we're going to use the radio frequency thermovoltmeter to make sure that our waveform distortion isn't severely affecting our instruments. And then we're going to go to the reactive power load to show what appears to be incredible quantities of energy by voltmeter and ammeter readings, but the wattmeter will give very little indication. So the first thing we'll do is we'll cut in the variable resistor bank and hunt for maximum watts on the meter. We have our red pointer left where we were at. All the way over. All the way up.
Louder, guys.
Okay, now observing the watt meter here, I'm going to alter the resistance from maximum to minimum, hunting for a peak in the watt output. So it does appear that our light bulb ended up being a perfect impedance match to the generator.
But now we will see what that does.
Leading the light bulb into the circuit for a visual effect. We're now going to energize our radio frequency voltmeter and check it against our switchboard instrument. Okay, our thermal voltmeter reads, I don't know if we can catch this on the tape or not.
Approximately
If you hold it still, we can get it.
66 volts.
Okay.
And this is reading approximately 62.5 volts.
So obviously the error is in our favor rather than against our reading. So our efficiency then is at least 108%. Okay, now what we're going to do is put in the energy storage or reactive load. We're going to start cutting in condensers here. Now we notice that our electromotive force is rising. Our current's starting to climb. We need our voltmeter. Get a shock off the case of the equipment. I don't dare energize the radio frequency voltmeter. The scope has gone off the screen, but as you can tell by approximation, it's now resolved to nearly a pure sine wave. Okay, now we got very high voltage. We pinned out the instrument. We got heavy current flow, but look at the watt meter. It doesn't read anything. Now, mistakenly, this is what people often misinterpret as free energy. But it's simply the reactive surging of energy between the capacitors and back into the machine and back and forth and back and forth. So we have basically two types of electricity then. We have the reactive electricity of energy storage and return, and we have what's called the real electricity of energy consumption.
Sometimes the simplest things escape the observation. Here's an experiment impedance matching a solar cell to its load. This experiment was done in the Borderland labs over the last several months, and we would have patented it if we had the money to pursue it, so we're giving this one free to the world. Here you go, folks.
And we have our solar cell input coming from outside in the afternoon here in Santa Barbara. And the tape here?
That couldn't be the end of tape, not even halfway anyway.
Go ahead. Pull your short circuit spark.
So we have our short circuit current here. Get our leads to stay put.
Hold it.
And we can see we have our little captured sun here. Now notice this is kind of a constant current spark, and we'll find that basically our solar cells tend to be constant current apparatus. Now in their application, they're connected to a source or a sink, you might say, of constant potential, the battery. Now if constant current has infinite impedance, and constant potential has zero impedance, then when you hook the two together, you have minimum power transfer. So obviously, we're not utilizing the solar cells to our best advantage. So we'll permanently hook the solar cells into our system here, trying not to get shocked.
How many volts are coming in from the solar cells here?
We'll be able to measure that. So now we're receiving about 96 volts, a little higher. There's no need to use our thermal voltmeter at this point because there's no waveform distortion with DC because there's no time function. Now what we'll do is we'll cut in a visible load and the solar cells are being put to work. But then we can also put it into our resistor bank and our instruments come to life here. Our watt meter is showing us how much energy we're consuming. I'll tune the resistance. And find a certain point for the output power of the solar cells is max. Now, we found in our research that this varies considerably with the light input. So in order to use the solar cells most effectively, a device connecting between the solar cells and the batteries is necessary to match the impedance of the system in order to facilitate maximum transfer of energy. Now, of course, this becomes rather complicated with DC because you don't want to use series or shunt resistances or any of these things because they will interfere with the operation by wasting energy. But fortunately, Tesla patented a number of devices commutating transients by charging and discharging capacitors through inductors where no energy is lost and the impedance is conveniently matched one way or another. Another method, of course, is the motor-driven variac and AC choppers. There's a number of possibilities to affect this conversion. The higher the voltage you use, the more efficient the process will be when using electronic apparatus. Basically, 90 volts would be about the minimum voltage necessary for a high-efficiency transfer. Of course, when we short-circuit the system or bring it down, then the ammeter goes up and the voltmeter goes down. So you find you really can't interpret what's going on from these meters as we've shown before, but it's the watt meter that's telling us what's happening. So that basically concludes this experiment.
Thank you, Eric, for a more efficient way of getting energy from the sun. And just to show that there's nothing new under the sun, well, today it's October 24th, 1987, and we're going to look at some experiments with something that Faraday started working on in 1831, what could be called the homopolar generator, although the modern variations couldn't be called such. It's been known as the N machine and other variations. And right here we have a copy of The Electrician from June 8th, 1888. And we flip it open here, and here we see a homopolar generator. And here's Mike Knox, who's built many of these machines, and he's going to point out a couple of the pictures here.
Yes, it seems that experiments were done by various individuals in the 1888 era on various types of what they were calling unipolar devices. And here's a picture of an apparatus that was demonstrating an effect of rotating a magnetic field in space, and thus the resulting an EMF that would occur. And as we flip through this journal that was copied, which is available at the local university, we see various apparatuses that have been built by various individuals to demonstrate the effect of the unipolar or homopolar generator. And also noted in the journal is what was called the Wimshurst machine or influence apparatus.
Well, that's the dielectric analog to the homopolar generator.
Yes, yes. And as we go through here, more of the mechanisms that were assembled. And this was a great little machine, the Wimshurst apparatus, demonstrating sparks that would be between these two electrodes, demonstrating dielectric properties of...
So that dielectric is also called electrostatic, so a Van de Graaff generator would be somewhat relational to that type of discharge.
And another demonstration of another unipolar device.
These are excellent articles for anybody that's really interested in doing this type of work. Just go to your library. This stuff's been on the shelves here 99 years.
This seems to be an experiment very similar to what is called the Dasgupta experiment held in 1960s, if I remember right. I'd be wrong on that. And there's a few more here at the back. Various experiments done. And here is an interesting apparatus that was built that seems to demonstrate various properties of the reluctance generator, the Wimshurst apparatus, and the homopolar generator. And an actual machine was built, as you see. And the end of the journal, The Electrician, June 8, 1888.
99 years.
And what we have for the next demonstration is a AC machine that we will demonstrate to you. But first, what we have is we have the new and the old. The old being the conventional Faraday disc, where you rotate a disc in a magnetic field, and then the subsequent studies that were shown also in this journal of 1888 of rotating magnetism with the disc and creating an EMF. And what we discovered was a way to create an AC EMF so that one could get rid of the problem of how to convert DC into AC. And an explanation. Right, Peter? Yes.
Basically, what we've done, Michael and I have worked together for many years, and we've run literally hundreds of experiments together. And we've always been interested in the early Faraday work. In his journal of 1831, Faraday showed that when you rotate a magnetized cylinder and put a probe at the edge and at the center or the shaft, that an EMF, a pure direct current of extremely low voltage and a high current, is produced. Both of us have worked with a gentleman here in Santa Barbara who has worked with this phenomenon for a long time. His name is Bruce De Palma. And we've both been very interested in this work for many years. The problem with developing this phenomena for energy production has to do with the fact that most of the appliances that we have today operate at about 120 volts and about 1 ampere. And this device is more capable of producing about 1 volt and thousands of amperes. So the question is, how do we get the energy out of such a device and make it useful for the kinds of equipment that our society uses today? Many of the experiments which have been done have seriesed these types of discs and created many, many disc brushes and compounded the mechanical problems of the device to the point where they're very inefficient simply from the mechanical loss standpoint. We decided we wanted to run some experiments to better understand the fundamental principle of how this phenomena was generating electric currents in the first place. And so we started building a number of discs. And to first understand the phenomena, what we did was, instead of using a big disc magnet, we just took one piece of magnetic material and just glued it onto one end and turned this disc and started looking at the outputs through an oscilloscope. And what we found was that there was a little lump every time the magnet went by our probe, that there was a little jolt in the current, and other than that there was nothing. So we came up with this configuration here, which we're calling the new one for 1987. I think we first ran this experiment last year, 1986.
Which must interject, there was Michael Knox, Peter Lindemann, and Chris Carson.
Chris Carson, who were originally in the shop when this experiment was run at first. And it came out of long discussions by the three of us over just what was going on. And at one point, we decided we didn't know at all what was going on, so we proposed this experiment, which was clearly not discussed in any of the literature before, and we basically thought that this was a completely insane type of experiment to run, because if anything occurred on this disk at all, it would certainly be self-shorted out, and it shouldn't have shown anything under current understandings of electricity. So we ran the experiment, and lo and behold, it produced an alternating current output, and we want to demonstrate that for you right now. We have here the device. We have a small drive motor here coupled to a disc. This first disc here, which has 4 rectangular magnets glued on, and just to make sure that the magnets don't fall off, we have another disc glued on the back of it here, and then it's wrapped in copper wire, which would certainly short everything else out if these discs weren't sufficient to short everything else out. So this disc is a total short around, and we have one brush at the center of the shaft here at the end, and another brush riding here at the edge of the disc at approximately the point at which the magnets come to an end, and these two probes going directly to the oscilloscope. We want to just basically state that the level of magnetism in this machine is extraordinarily low. The speeds we will run it at are also quite low, and but we wanted to demonstrate that you can produce an alternating current waveform directly out of a disc type of device of this nature, and that more research should be done in this area, because this is a very excellent way of getting the power out of a disc type of device that produces very high currents and low voltages, because the output of this can be put directly into the primary stage of a transformer and the voltage raised directly that way, without having to chop the DC with all kinds of mechanical solid-state apparatus. So we can just turn the motor on, and instantly the oscilloscope starts showing the waveform. If I turn it off again.
Let's also put our protective barrier on.
Oh yeah, just to protect ourselves in the shop, we take the precaution of putting this basket over the device, because these are ceramic magnets, and we've used epoxies and other things, but this is, to be sure, a test device which has not been adequately balanced or protected in any way to keep the magnets on the device. We're creating very high centrifugal forces. And we're going to just turn this thing on now and run it at a very high speed, which may or may not destruct the device on camera here, but we hope it won't. We've run it up to certain speeds before. And you can see the waveform here. Coming directly off the disc.
Can you explain where those meters are reading also, Peter?
These meters are reading the input power to the drive motor. So these meters are not significant under these circumstances. The only thing we're looking at here is the fact that you can create an AC signal directly off of a disc device of the style that Faraday originally discovered in 1831. Now this is the typical arrangement whereby we're reading the potential difference between the center here at the shaft and the edge, the typical way the Faraday device was used. Now we've set this system up so that we can change the position of the pickup brushes to a number of different locations to show that this phenomena is also capable of being produced in a number of different ways with this apparatus. As Michael is changing the location of the brush here, I'd just like to say that basically what we're doing, we had, for the first test you just saw, we had one brush on the shaft here, and another brush riding on the disc out at this location, so that as the different pole faces move past between these two brushes, they produced EMFs in opposite directions, as would be expected. What was interesting about this is that it produces any EMF at all, because all of the points on the shaft that would be producing these things are in direct short circuit with each other at an extremely low resistance.
Peter, is the frequency deemed by the RPM?
Yes, it's direct. It varies directly with the speed of the disc.
For one thing that I'd like to point out is the fact it was noticed on the oscilloscope by observation that the amplitude was nearly independent of RPM.
The amplitude varied at much less rate. As we sped up, the amplitude was getting slightly larger, but certainly not, it wasn't a linear rise.
So it's a direct departure from the law of electromagnetic induction.
Okay. So what we've now done is we've placed one brush on the perimeter here and another brush on the perimeter here, which would be one brush here, one brush here, and one brush here, both on the perimeter. Now, there's an absolute dead short circuit right around the outside here that wouldn't have to go through any magnets at all. And it certainly is, we would all be hard pressed to explain to you why any EMF should be present at all under these circumstances. So let's turn it on and see what happens.
Glass shield.
Thank you, Eric, our safety director.
Yeah, third safety engineer there.
And as you can see, you knocked the brush.
This is general lab operations here. What do you estimate the cost of this experimental machine was just to build?
Oh, most of these things are built from junk and stuff that we've had around the shop over the years. The cost of keeping this shop open over the years has been an astronomical amount of food money.
You don't get funded for this research?
No, we've never been funded to run these experiments. Michael and I have worked together for 5 years and never been funded.
Do you ever expect a payoff from it?
I'm not into predicting the future. But anyway, what we would like to do...
You just like to see the equipment work.
We're here running fundamental experiments in physical space.
Right, so product's not the end run. You're experimenting, you're research.
Once we understand the phenomena that we're dealing with, hundreds of thousands of commercial products will be available. But there's no sense trying to run for a product when we still don't understand fully what's happening. So anyway, let's take a look at the output from this. And as we can see, the EMF coming from this arrangement is slightly off the screen. We have to raise the... so the EMF is even greater when we put the brushes at these locations. Your guess is as good as mine as to why that's true. Now there was another experiment which we're not set up to do that Michael and I originally did in the original set of experiments, and we put both of the brushes, instead of out here at the perimeter, we put one here, one right here on the shaft, and another right here on the shaft, almost touching each other. And when we ran the machine, we got the same fundamental output as what you just saw, as if the brushes were way out here on the perimeter.
Same amplitude of the wave?
Same amplitude of the wave, same current. So there's...
What's the amount of power being generated here, actually?
Well, in this particular device, this is a very small disk. It's a very low speed. It's a very small amount of magnetism. Quite frankly, the amount of power under this demonstration is quite low.
But were you successful in heating up a wire?
Oh, we were very successful in heating up a wire.
Okay, now what was the gauge and length of the wire?
The gauge and length of the wire, I don't even know whether we have that. Let's see. What we did was we had this apparatus right here.
Okay, a current transformer, CT.
This is two brushes and a current transformer. And we can duplicate this experiment by hand right now. What do we have to do? Measure the resistance in this, hook it to the scope.
No, it has to be short-circuited and measured with radio frequency milliamp meter. Should take a little bit of time to set up, but you said that you witnessed heating of a conductor. Was it that conductor that heated up?
This was the one, the very one, holding in your
Now
hand.
what gauge is that conductor? About 8 stranded? Show it to Chris. He would know the wire gauge right off.
About 10 gauge.
10 gauge stranded.
Yeah.
Okay, and the length is about, what, 6 inches?
5, yeah, 6 inches,
and
yes.
about roughly how hot would you say it got?
You were holding it.
It became uncomfortable after a while.
Okay, that's about 110 degrees, 115 degrees. So if anyone wants to take the effort with the length, the gauge of wire, and temperature rise over a period of about how long would you say?
Oh, 10 seconds.
10 seconds?
15.
So that would give the inquiring member of the audience that wanted to perform the calculations the amount of energy its device produced.
So you feel that
We calculated that there was a number of amperes running
So
over.
for 10 gauge to get noticeably warm that fast, the current would roughly be 100 amps.
So you believe that larger, well-built models of this are definitely avenues of real research?
Oh, yeah.
Absolutely.
Oh, absolutely.
Without a doubt.
Which would resolve some of the problems of the DC motor technologies that are trying to be developed to be harnessed to the end machine, homopolar, unipolar technologies. It seems that the process of that everybody seems to be headed into has narrowed the science, and instead of branching outward into other aspects of the disk technology, we have discovered a way to be able to resolve the AC problem, which has been in, people have been trying to discover that quite some time. Even in the 1888 information, questions were risen, why can we not create an AC waveform out of this disk technology?
Wasn't that the problem Tesla resolved with the complementary apparatus, the multipolar machine? Was the same thing. For many years people struggled with direct current, and then all of a sudden AC was the way out.
Exactly.
Now we have an
Exactly.
analogous situation occurring with a different technology.
Right.
And it seems that the disk technology will not be a generator of electrical energy, but a phenomena that, when harnessed, will become what I would call an engine of power, which would then subsequently be the motive driving force, say, of an apparatus like the parametric transformer or the reluctance generator, as we call it. Any comments, Peter?
I feel that this phenomena is definitely in its infancy. I have not seen any books or technical papers on producing a direct AC output from a disk type of generator before. And I don't know of any electrical theory of induction which would suggest an explanation as to the kinds of behaviors that we're seeing here. Do any of you electrical engineers have any comment on that?
Have you tried doing this without the electric motor? Like with an air-driven motor or...
No, but I can assure you that the signal is related to the disk, is from the disk. Absolutely.
That would be one experiment to pursue.
Oh, absolutely, absolutely. Again, the crudity of the experiment is based upon the amount of money that we do not have.
Well, what do you feel would be a realistic number to begin some
Could we
basic...
demonstrate to you that, I mean, if we turn the power off to this generator and still see the signal as it slows down?
Because this is not a permanent magnet.
Right, it's not a permanent magnet. It has a field and everything, so when we turn it off, it's completely off. And and as it slows down, the signal is still on there. Would you believe that it's really from the generator and not from the motor?
Are you going to spin it by hand, maybe?
No, we'll bring it up to speed with the motor and then turn all the power of the motor off as it's spinning.
Right, and the inertia will
And the inertia will carry the thing and continue to produce the signal on the oscilloscope.
Couldn't you still being generated by the spinning motor?
Eric, you feel that there
No,
would be...
because it would be in an open circuit, all those fields would
Well, that's a
collapse.
valid experiment. Obviously, closer detail the apparatus is necessary, but it'll slow down slow enough even with the drag.
Go ahead and bring it up higher, 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 higher.
That's fine.
All right, good.
All the power to the motor is
All
off.
right, the watt meter reads 0.
Yeah.
Let's do it again with the camera on, the input watt meter and input amp meter.
Okay, I got everything in there in this one.
So this is just to,
Bring it up higher, Peter.
this is just to suggest that the power that we're seeing here, the signal here, is being generated by the generator and not the motor. The watt meter on the motor is 0. The signal is still coming from the generator as it slows down.
That looks pretty good to me.
No, it would be interesting to figure out what the critical speed is that the EMF suddenly starts to drop. Because the EMF appears directly independent of the frequency here, which is definitely novelty with regard to the law of electromagnetic induction, which involves direct proportion to rate of change or per seconds.
As far as the height here,
Exactly. One other thing I'd like to point out too is in fact the distortion in the waveform indicates triple harmonic components, which when you start to study this mathematically become the fundamental pattern of so-called free energy. The fundamental frequency exists with regard to volts or amps, as we've shown, don't directly correlate with what we're interested in, and the quote Steinmetz are mathematical fictions. The power is a double frequency quantity, or second harmonic, and is what we're normally looking at in electricity. The triple harmonic component, which has received very little attention in theoretical analysis, is the energy component, energy harmonic. And you'll notice, the viewer may notice that the waveform of this apparatus was very similar to that of the reluctance machine. These are very interesting things to think about for a while.
Michael, you're a design engineer. What type of dollars do you feel it would really take to actually pursue this? Say if, even on a small scale, not a big industrial scale, but for somebody who wanted to just try and build a better model and demonstrate further principles realistically?
Well, realistic in today's costs of maintaining laboratory, machining costs, design time, in a period of 6 months' time, but just to do some basic experiments, one could consume $100,000 quite easily.
So it's an expensive pathway to go.
Yes, 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 but billions for war, 0 for peace. I find that
Well,
is
don't we have
a
free
concept.
energy already? Nuclear power.
Unclear technology.
Right.
unclear.
Well, this is a very interesting device here.
A number of experiments need to be run, which we have been doing through the past years. And again, the thing that stops all of this is that liquid thing called money. So that coherent results can be pursued, correct documentation, correct metering devices put on each apparatus so that each subsequent test and demonstration can be properly documented.
Well, that basically means that free energy is not going to happen for free.
Oh, absolutely
Absolutely not. Absolutely not.
Free energy research costs a lot of money. This brings to an interesting point. A lot of people who have been buying various books on the market about free energy think that they can just buy one of these books and launch off in their spare time and build a free energy machine. That's a myth. And for those of us who have been involved in this research for many years, just to give you an idea, this device that we tested earlier, the parametric transformer here, cost Mike and I, over a period of years, approximately $20,000 to build and test. And
Out of our own pocket.
out of our own pockets. We did that research while we slowly went bankrupt and ended up having to abandon the research periodically and pick it up again later.
Is it not true that many free energy researchers often eat out of garbage cans and live in bushes?
We have known some who did, yes.
No, I have lived in the street and have pursued putting together the apparatus that you see here in the corner and other apparatuses that are in storage. It seems to be most intriguing the fact that people do not understand the amount of money necessary to be generated to do this research. And yet, presently I'm working for a job building a secretary's chair that tens of thousands of dollars are being invested just to build a secretary's chair to make her posterior more comfortable. And yet people do not understand why does it cost so much money to do the alternative sciences.
It costs money to do it right. Hard science is hard work, and as you can see from all the books and all of the claims that have been made by all the various different people that we refuse to mention, that so little hard and good science has been done on these experiments. If somebody's got a real free energy machine, it's either running by itself and producing something for it, or it has some input and some output. If it has some input and some output, if it's electrical, the bottom line test is the watt meters in and the watt meters out, and the differential watt meters showing the incremental change between the input and the output. And that's what we tried to show you here today. Watt meters in, watt meters out, the straightforward math of it. We gave you an excellent demonstration of the kind of rigorous procedures that you need to develop for yourself to test your own free energy machine if you ever get your hands on one.
It must be noted that in the present economic situation of the planet, this country, the stock market, as things start going for the change, because change will come about, money is going to have to be procured to be able to allow this alternative science in before it's too late.
It will be much easier to build these things while the economy is still fluid than it will building them out of the dumpster trash of some bygone age. So we'd like to get on with this work, and we hope that you all support Borderland Sciences Research Foundation in maintaining this laboratory and keeping the real work up. But for the finale of this show, we'd like to turn it over again to Eric, who's going to demonstrate some of his work with the Tesla technology and some extraordinary systems that he has put together.
Thank you, Peter.
Thanks, Mike.
Okay, thanks, Peter. Well, we've covered pretty much thoroughly what can be done with magnetism. Now we're going to get into the other side, the dielectric side of electricity. Now this side's a little more unexplored, and the stuff we're going to show you here is early in development. We haven't been able to complete the construction of the larger apparatus due to the unavailability of parts right now. But we have a little miniature model working here. But to start with, we have a very simple device to produce a very intense dielectric field. We can turn this thing up here. You want to go over there first?
Yeah.
This is what's called the voltage multiplier. It multiplies an 800 cycle output of an ignition coil as a step-up transformer being powered by an audio amplifier. Multiplier chain brings it up to, at this point, about 60,000 volts, even though because we're having problems in the apparatus, we're not getting the full 150,000 volts that this thing's capable of producing. But some of the effects will be noticed. As you can see, it springs to life.
Those are small non-conductive threads on the top of the column. Watch the threads when I short the device out there. Get over on this.
Okay, now what's happening here, okay, these are a string of capacitors quite similar to the other capacitor we were using in our previous experiments over here, the mica capacitor. These are ceramics, which are a little more efficient. Just make sure this is fully discharged here. Now you notice a bright blue spark in the middle, and it's often taught that this spark consists of the flow of charged carriers called electrons, and there's no action outside of the spark. Well, as we just found out the hard way, but of course is well known, wasn't shown on the videotape, so we lost a piece of equipment. Now, this was due to an interesting phenomenon, something that's not generally known about dielectric discharges. Now, to step back a bit, there's a phenomenon called saturation that occurs in magnetism. And when you saturate a magnetic material, it will permeate the magnetism up to a certain point, and then all of a sudden it'll stop, and all excess magnetism is thrown outside of the region of induction. But what this spark here represents is dielectric saturation. And the medium in which the induction occurs saturates to the point where it sucks the lines of force in to such intensity that you get a brilliant blue flash. Now, what's happening is these strings indicate this space is filled with lines of force around this apparatus which terminate on all so-called conducting surfaces. And when this discharge occurs, all these lines of force, which of course are most intense near the point of discharge, start to produce saturation at that point, and then when the saturation occurs, all the flux flies into that point, unlike magnetism where it's thrown out, and produces very significant currents. I would say the current flowing to the surface here, even though it only lasts for a microsecond, would be conceivably 5 to 10 amperes. Now, we have an interesting situation here. We're taught that amperes have to flow through conductors by electron flow. But we're going to find quite shortly that all that stuff is just totally incorrect. Now, what happened is our other test oscillator was transistorized, and it's very risky to use transistors for this business. And I connected the amplifier up in the standard audio engineer fashion, neglecting to consider that all these lines of force were terminating on it, and it went bye-bye. But so be it. So anyway, we got a vacuum tube unit here, but this is what's going on. Now, with lightning, it's the same way. It's not a bunch of electrons jumping from the sky to the ground, or those that want to argue that the electrons are jumping from the ground to the sky. None of that's happening. What's happening is in the so-called Earth ionosphere waveguide, where it's actually a giant parallel plate capacitor, you have these lines of force rapidly converging into the region of saturation. So you have these waves flowing into the discharge, and as Tesla found, when they hit the discharge, they bounce back out, circle around the planet, go back into the discharge, and you get the so-called standing waves. So this device serves as a pretty good indication of that very simple high-voltage DC generator. Now, when we didn't make the spark, the thing was called a direct current generator, but at the instant of the spark, it produces a new type of current called impulse currents. Now, with magnetism, it's so slow and sluggish, usually you have to deal with sinusoidal type of phenomena, unless you go for quick open break discharge like we did with the radar choke, and even then the self-capacitance tends to produce ringing and sine waves. But now we're dealing with a new type of waveform, transient electric waves, which last for insignificant periods of time. You might say that the mirror image of direct current, which lasts for infinite periods of time. Where direct current would be called a scalar waveform in the dimension of time, the impulse current would be called an anti-scalar waveform, which, interestingly enough, what people are presently calling scalar in the popular science field of today is actually the anti-scalar wave. So what we're going to do is we're going to change our setup, and then we'll get back and show you what happens when we put these transients into a resonant situation. Okay, what we have here is a little AM transmitter that we've built up, this being the modulator, this being the oscillator, and this being the power amplifier. And then, of course, we have various power supplies built in here. We have the main plate supply down below, which we used for earlier experiments, and then we have our low-level auxiliary power supply here for the oscillator tubes and what have you. Now, you notice a little corona coming off of this here. What this is a little midget Tesla coil, a little model of large units that we'll see later on in the tape. And this right now is resonating nice and strongly at 6.600 megacycles according to the oscillator. On the R390 at 6.575. I know this runs a little high, so our shortwave receiver over here is giving us our actual frequency. So calibrating this, it would be 6570 from where the dial's set on that. Now what we're going to do here is show some rather peculiar properties of dielectricity that have never really been seen before. We can do, so of course if we put wood near this, wood starts to burn. Now this is a continuous alternating sine wave that we have here. We'll have Tom blow the fire out. I have to tune for the increase in capacity. Okay, well notice it starts to produce some rather tree-like formations. Now we'll use the music to introduce transients on the system and help facilitate these little forms that we're going to see on here. I see one of our tubes is getting a little too hot. Now you notice you actually can hear the sound of the music coming out of the spark. Find a suitable point on the wood. Blow.
Can you turn it a little bit more towards the camera?
Now this piece didn't work out too good. But I'll bring it up to the camera and start to see.
If you just hold it near at the same location as the spark gap.
You'll see some forms starting to appear. Little geometric patterns are starting to be burned into the wood. We'll try a piece of particle board next. Let me switch the record here to a point more convenient as far as waveform goes.
Eric, is there a reason why you chose Bach?
Well, organ music's filled with sharp transients, and of course Bach was the master of the organ, so we have a lot of that on hand here that we listen to. Yeah, I notice I have to keep on retuning the oscillator to compensate for the decrease in frequency as the burnt spot grows. Let's see what we got here.
Doing pretty good. Living on it.
It's not particularly typical though.
That's about the maximum size growth we can get with this. Let me try another. Hey, we have another piece of particle board. You move it.
Show that one to the camera.
So you can see in this piece of wood here we have various. That was the best one that we got so far in an earlier experiment. What we just did was this one here. It doesn't really appear too regular.
If you hold it so that we don't get such a yeah, right, there we go. Turn it a little bit more towards the other way, the other way.
We have another piece of particle board.
That works much better.
Yeah, if you could turn it over now.
Wimhurst.
Turn it over again.
Can someone give me the other piece of particle board?
Oh,
Have that.
And turn it, yeah, tip it that way. Great. Hold it right there. Notice that one.
Like I pointed out earlier, this apparatus is really fairly powerful enough to do this.
You'll notice how the videotape again is being distorted even from across the room by the emissions from this coil. Very similar to some of the first experiments that we showed. This is a transistorized system that's approximately 8 feet away from the coil at this point, and the signals coming from the coil are distorting the internal circuitry.
Eric, on previous experiments, when you use lead and lag power supply on an apparatus similar to this, didn't you have like tree branches and tree roots?
Right, that's one thing I'd like to point out, we can't really quite see here, is that the discharges when the thing was tuned to the magnetic side of the cycle, in other words, the frequency brought down to such a point that the device appeared as a magnetic inductance because the capacitance wasn't able to fully partake. In other words, it was off of resonance on the magnetic side. You would get branches that would appear as this discharge evolved in form. This all in free space. Then you switch above the resonant frequency of the coil, so it's operating more on the dielectric side than the magnetic. You get a long taproot that would stand up with the little root hairs sticking out. Now this is interesting because the dielectricity is directly correlated to the roots, or the underside or dark side of the plants, and the magnetism is attributed to the branches or the top sides of the plant. And this is carried one step further when you start producing discharges in plasmas, or you can even see in free space if you look at the discharge with a fluorescent lamp or some kind of broad illumination behind it, you will see not only are there the sparks that glow, but there's another system of spiraling sparks that absorb the light from the fluorescent lamp behind it. So there's a complementary pair of discharges working with each other, one luminous and one anti-luminous. And when we use bulbs, this is even more pronounced. Let's see if we can get a better piece of wood going here. Okay, need modulation again. There we go. We just needed a higher modulation rate. Our tubes are running away. We better cool down here.
Okay, it's only a Nikola shot.
But we did it, folks. We got one.
And one of the things about these is,
hold it down a little bit so it doesn't reflect so much. Yeah, there we go.
as I've observed these various discharges on the different coils, I've noticed the tree forms below resonance and the root forms above resonance. But another thing I've noticed is at different frequencies and pulse widths, you get the discharges look like various vegetation. You can see desert vegetation or lush vegetation just by varying the pulse width. And this shows us the plants are themselves discharges which are coming out of the ground. You know, just as this circuitry here is developing something, a discharge coming out, the plant is a discharge of the energy from the earth. And you can tell the general character of the type of earth around here by the type of plants which are discharging into it. So this type of apparatus here opens up study into many fields, not just electricity. It shows, you know, the whole living fields of
Basically,
life.
what we're getting into here, we'll find later with the four-quadrant theory of electricity, is we're getting into the very archetypal forms of space itself. We'll do one more burning here. Now that we know that we have to run greater than 100% modulation to get the effect, we'll try this again. Because it has to be transient electrical waveforms. Sinusoidal electrical waveforms will not produce this phenomenon.
One of your volumes
Life here. getting it?
Yeah.
Oh, perfect. Just let it go and go and go.
Leave it on there.
So I can get a good
Up
shot.
until I got
Got it.
meltdown in my
Got it.
tubes here.
Got it.
Okay, I have to let the tubes cool down. We're going to melt the glass. Now the size of these, of course, are proportional to the wavelength of the oscillators that we're using. So at this frequency, we really can't expect a growth too much bigger than this.
Do you have any of the other ones here from the other experiments?
No, most of that's gone. But nevertheless, I think this points out very clearly what's happening here.
So different types of music would give you a different pattern, right?
There's actually very little difference.
It all looks organic. Just like you see how every bush grows a little different. Each one of these is
It's all
individual.
based on, these are all based on the golden ratio. It's proportioning. This is all 5 proportion, just like all organic forms are. So as long as you have music that produces abrupt transients and not sinusoidal waveforms, then this phenomenon will appear. If you just use a carrier or you just have sine wave modulation, it's much less intense. When we were running our modulation below the distortion level of 100%, the phenomena wasn't very pronounced, but when we ran above 100%, it really aggravated the transients produced by the music and caused blocking in the tubes and what have you, so that we started getting pulses and spikes. Now, you'll often find old photographs in books on cable insulation. And you'll find beautiful patterns burned into insulators and pieces of cable paper and other types of material that appeared in power lines, which used to be all ungrounded systems years and years ago, and they would start producing these radio frequency transients when one insulator would spark over.
We did publish that one picture in the Journal of Borderland Research, the cross-section of the insulator that was hit by lightning and showed a pentagon shape.
Right, there's a perfect starfish shape, which again, golden ratio of division by 5 of the circle, blasted right through the insulating wax paper sheet and the lightning arrestor stack. Very regular 5-pointed star. Now, with the big apparatus, we ran our prototype of this, but we're still in the process of rebuilding it now. But when we did the tests, and we might be able to get some clips of this later on in a future video, we did get video documentation of part of it, even though it jams the video apparatus so extensively it's nearly impossible to see too much. When you start using light bulbs, and we have a few of them here, now the frequency of this machine is so high, I think the light bulbs will be dampening it down. Let's just give it a little try.
Aaron?
Anyway. Yes.
Should we dampen this thing here a
Yeah,
little bit?
but let me see what I'm doing here first.
Okay.
Try this other light bulb.
You want to tape that to a handle?
Burned out.
All right.
You want to tape that to a handle or something? Or?
Oh, no, I don't need to.
Okay. Michael, just let him see how it's going to work before you pull it. Can you explain this dead spot in the fluorescent light?
Okay, now we have...
Yeah, could you pull that, Michael, so you can see this?
Let's see if we can find it here. There we go. Now where the two dielectric fields cancel out, you notice there's a little spot appears in the light bulb there, a point of cancellation. Now when the coil is operating perfectly distortion-free, this little notch will be right in the middle. In this case, we've got our pronounced second harmonic in the system here, being that the center tap of the coil is not neutralized. So we're off to the side a little bit. Okay, now this is the region when we get the flux intense enough that it's best to put the light bulbs. I don't know if Peter can swing around to get the bigger coils stored in the corner. Can you get a quick shot of the bigger system? Why don't you pull the extra coils out of the way there, David, and we'll get a good shot of the coil. You'll see the larger apparatus we did our initial experiments on. The power unit is being rebuilt right now, so we can't show this at the present time. We'll get into a more detailed photographic analysis of this later, but just to get a quick shot for now. Now you notice this looks a little different than the Tesla coils that you normally see. First of all, it's double phase and not single phase, and the coils are flat rather than wide.
Steve, could you just walk up to it so we can get an obvious sense of how big this thing is here? There we go.
This is more than a Tesla coil, isn't it, Eric? This is...
Yeah, this basically we might call a cosmic induction generator. What we're using is the Tesla coils as a component. The Tesla coils are monopolar electrical devices, and operating two of the monopolar electrical devices back to back produces this strong notch that we see in the bulb here. Now, when we put the large incandescent bulbs in this region, and we have a displacement current flowing from end to end of the coils here, we get that up to about 5 or 6 amperes of current. Put the bulb in the dead zone, or the region of minimum electromagnetic activity, then we start getting a lot of various forms appearing in the bulb that look like suns and stars. And if you can work the bulb long enough, a galactic formation will actually appear in the bulb. Now what's interesting is the vortex action in this galactic formation is such that you might say it's taking primary substance and sucking it into the vortex, but what happens is it produces the effects of ponderable matter as physical pressure on the walls of the bulb. Now what we've found is that the bulb will actually start to bulge out as the glass gets hot, rather than collapse in, even though there's a very significant glow discharge going on in the bulb, indicating that the plasma has to be operating at a low, very low gas pressure, but you have the physical effect of pushing. Now what happens is it'll rupture, and this purple glow will come shooting out of the bulb sounding like compressed air. So we have something that appears to be an energy to matter conversion, or a very unusual repulsive force. Now the demonstration I gave in Colorado not too long ago, when using very sharp transients produced by spark gap apparatus rather than vacuum tube apparatus that we have here, you can actually feel a field of repulsion around the bulb. It actually tends, you can feel a slight push against your hand. Now this bulb here will probably, no, this bulb is atmospheric pressure. So we'll have to try another one.
This one here probably. Let's see.
Well, that was the one that we blew this one out in Los Angeles last week. Let's try the one that looks real dark. Now what's interesting is the bulbs that are usually most failed inside work the best for this kind of stuff. I think our...
You want to rig this thing up? And just turn it?
Yeah, let's turn that on. We'll take a quick break here and change our setup.
I got one bulb that works.
Let me know when you're ready to start.
You're on.
Okay. Yeah, this is basically what starts to happen in the bulb. We have a much longer wavelength apparatus here. This one operates at about 380 kilocycles. So it's not very affected by loading. And you can see the branch-like formations. Now, these lights have become very popular in the marketplace. But with a higher power apparatus, we have been able to carry it one step further with things we can't show here, but we do start to get the effect. Now, I don't know how this looks in the TV camera. Can you see a kind of a spherical boundary around the filament?
Yeah.
Now what's interesting is, as I increase the power, it's almost like a ball in there is keeping this thing in a boundary. Now that's a very interesting property of these plasmas, is they tend to have very well-defined boundaries. And when the power is brought to an appropriate level, these little boundary zones, which look like little suns and stars, will form spiral and nebulous formations inside the bulb. Now what we can do is increase the power, becomes a little more visible, and then we'll reach a critical point where it busts through the boundary. And then the hysteresis, we have to bring it down even lower, and then come back up again.
That's fascinating, Eric. The boundary is quite visible on the TV.
It comes out quite well.
Oh,
Yeah, the boundary's broken there.
Maybe we could do it, turn these other lights out, because I think
Yeah, can you just hit that switch over there?
The field. You can see this field's weaker than the other unit, but it has more current behind it. But nevertheless, we get it out. We have a notch zone appearing in here somewhere, which is interesting because these two coils are operating in phase rather than out of phase, but all the metal around is influencing our effects. Yeah, now the sphere is very visible. Bring the power down. Notice as I increase the power, the sphere remains basically the same size. Now it's starting to go through. Won't go through now. Don't have quite enough power over. The boundary's been strengthened apparently.
Tune it a little bit. You must
Oh, I'm hitting the tuner rather than the variac. There we go. Again, I'm raising the power, and it breaks through, and I have to bring the power down much lower than the point it started. I bring it back up again.
Yeah, it's very visible. Can you bring the house lights up again?
Okay, let's experiment now. Okay, here we have a resonant coil with a very loosely coupled excitation loop tied into the output of our oscillator that we've been using in our previous high-frequency experiments here. We have the diagram on the board where we have our AC generator, this being the oscillator, or frequency generator, or a little magnetizing loop, or we might say our primary coil, and then our resonant coil. Now, in order to have the resonance of a quarter wavelength, we have to have a dissimilarity of impedances between the two terminals of the object exhibiting the resonance. Now what we have here is we have a complete open circuit on one end that just dead ends to a piece of Teflon with a discharge point on it with practically no capacity. And then on the other end we have a length of wire with a little bit of self-capacity to give us our imbalance of impedance. A very slight, but nevertheless a very definite imbalance of impedance. Our meter is a Simpson 260 on 2.5 volts AC, but as we see, the leads don't really need to be connected to measure this. It just becomes an RF field strength meter, and it's showing the field around this. Okay, now what we're going to do is we're going to sweep around, and the camera will show what the meter does. And we can see the coil exhibits a very sharp resonance. And I just go off a few kC on either side and it drops right down. That's 0 kC, 5 kC, and 0 kC. So we can see without any capacitor hooked across the coil, it's a very effective resonator. It's basically a 10 kilocycle wide coil. Now, what's normally done is you take the length of wire on the coil, which in this case is 2,816 centimeters. And what you do with this length is, being that it's a quarter wavelength resonance, then a full wavelength has to be 4 times the length of the resonator. So we multiply by 4, and that gives us 11,264 centimeters, which would be the effective length we're dealing with. Now, the velocity of light has been determined to be 3 times 10 to the 10th centimeters per second. Now, of course, this is a very controversial subject these days, and we might say that it's just simply the ratio of a dimension of space to a dimension of time, and it's not really the velocity of light, and we're going to see how this breaks down here. Okay, now we've been told this is the velocity we should use to compute this. Now also we've got insulation around the wires, and we have rods that have a definite dielectric constant above unity, so we have to consider that we're only going to be propagating at 90% of the velocity of light, which is the basic approximation used for transmission through wire pairs or anything where you have reasonable amounts of insulation around the wires and insulators holding the wires at intervals repeating. So what we'll do is the frequency then is the velocity divided by the wavelength. And if we calculate it by this method, we get a frequency of 2.397 kilocycles per second. Now this is the wavelength due to the velocity of light. Now we look at our oscillator here, and we find that the oscillator reads 3.655. Now just to make sure the oscillator is not screwed up, we'll go over to the shortwave receiver. There we are. The receiver says 3652, so we have a slight discrepancy, but not too much. As we found, where this actually reads a little high, but it's within close enough. So if we take the ratio between these two, we find out that we have an effective velocity here that must be 152% that of light. Or we may conclude that the velocity of light has little meaning in calculating the quarter wave resonance of coils. Now, many people are saying that the way to compute this resonant frequency is by the velocity of light and an associated quarter wave formula. But you will find that the coils they're working with are very heavily saturated with dielectric material, such as plastic tubes or cardboard tubes that the wire is wound on. Plus, the length of the coils is such that the wave is very severely distorted and tends to snap it into another mode of oscillation. And as we know from studying Tesla's notes and patents, that he always preferred flat coils. Now we have some Tesla resonators which we built here, that we've been doing experiments with. This is what Tesla had in mind, was this type of object. We can see it's not much coil this way, and not much coil, or a lot of coil this way, so we have a flat spiral. Tesla did most of his pioneering work with that. The coils that are used today will be more of a form of this coil, which is a lot different. Notice heavy dielectric everywhere, very long extended coils. Vast departure from Tesla's design. Now, looking at the pictures in the Colorado Springs notes, you'll see that Tesla used a coil that had a width equal to the height. Okay, now by experiment, and I have derived an engineering formula for actually computing what frequency the coil itself will resonate at, even though it's up to the reader to use the appendix in the back and the equations provided by Miller for computing the effective external inductances capacitance, was always pull it down. The theoretical multiplication factor here is 1.87 times the velocity of light for an equal length to width, or a unity ratio of width-length coil. Now, if you look in the Colorado Springs notes, you find that Tesla's extra coil had an equal length to width. And 100 turns rather than 44 turns we have on here. 100 turns appears to be about the optimum subdivision of conductors. The radio frequency transform which drove this thing was around 80 feet in diameter and very flat and squatty. Now, we do see in the photograph some little test coils of great height, but these were to exaggerate particular harmonics, and Tesla used them to determine the harmonic content of his waveform, and they participated very little in the actual functioning of the apparatus. One thing that's not generally known is the coupling has to be very light on these coils. Now, we have to get this pretty close here so we can get the meter to move, but you find as you move the coupling farther away, bring the dissimilar impedances closer and closer to similarity, but still having a difference, then you asymptotically approach your calculated magnification over the velocity of light, or multiplication over the velocity of light, of 1.87. But at that asymptotic point, your coupling is so light that you can't get in to measure it. And another very interesting phenomena occurs is the Q, or magnification factor, of the coil continues to increase as you loosen the coupling until the resonance becomes so sharp that you can't find it on your oscillator. Now what Tesla did is he struggled with this for a long time, as he always was killing the oscillation in his extra coil by direct connection to the secondary. So what he finally did, but it's not generally known, but you can see it in some of the photographs and there's scant reference of it, is a very long, like, delay line was connected, a flat, very long skinny coil, not really resonating in a quarter wave mode, but a half wave mode, to decouple the two coils so the extra coil was able to operate in a free resonance condition and produce the most significant magnification. So again, we find departure from the normal rules and things that are taught to us in school. Now next we'll get into the four-quadrant theory and how all these things that we've talked about so far tie together into a generalized archetypal form of electricity.
Well, we've basically run out of time on this video, and we've decided to do volume 2. But in closing, we'll take a look at what we know here. Everybody has one on their house or business. It's known as a kilowatt-hour meter. And what this does is that kilowatts shows the amount of energy consumed. And of course, we know we pay for that, so that shows that energy and is in the dimension of dollars. So when you get free energy is when this goes backwards, and in volume 2, you will see it go backwards. So now I'd like to thank Eric Dollard, Peter Lindemann, Chris Carson, Mike Knox, Dave Franklin, and especially Steve Ellswick from the International Tesla Society, who flew out here 2,000 miles to see this demonstration. And if you're interested in more information on the International Tesla Society and their upcoming symposium next year on July 28th to 31st, 1988, you can write to this address here, the International Tesla Society, 330A West Uinta, Suite 215, Colorado Springs, Colorado, 80905-1095, USA. And they're also publishers of books and the Tesla newsletter. So if you're interested, write them and get in touch and join in the action, along with Borderland Sciences and the International Tesla Foundation. Thank you for watching. I hope you enjoyed your trip.